Welcome back to Topic 10 for Algebra 2, Absolute Value Functions. In this video, we're going to learn the transformations that an absolute value function makes, as well as how to graph them. So first, let's learn the parts of an absolute value function. We learned about this a little bit in Topic 9 when we dealt with parent functions and their transformations. Whenever we have our a, our value out front, and if that value, the absolute value of it, is bigger than 1, then this is called a stretch. And our function on the graph actually seems narrower. If our a value that we're multiplying is between 0 and 1, or the absolute value of it, instead of having a stretch, we have a shrink, or a compression. And visually, you'll see that our graph gets wider. Now, if this is a negative a instead, then it means we are reflected over the x-axis. Perfect. So that's our a. Now, whenever we deal with h and k, this is actually the vertex of the graph. So for instance, if we have the function f of x equals the absolute, 2 times the absolute value of x minus 3 plus 5, then our vertex here is 3, 5. So notice again how this is x minus, but this is a positive 3 because we are subtracting a positive 3 right here. Now let's graph the parent function. So again, we were exposed to this parent function in Topic 9. So our parent function will look like this. Our vertex is always at 0, 0. And if we plug in -2, we'll get out 2. If we plug in -1, the absolute value of -1 is +1. If we plug in 0, the absolute value of 0 is 0. If we plug in +1, the absolute value is +1. And if we plug in +2, the absolute value is +2. So now we can graph this on our coordinate grid. And if we just continue, we'll see we get this like V shape here. And actually, if we took our function and if we fold it in half, I should say, we'll see that we actually have what's called an axis of symmetry. At x equals 0. So at the y-axis, if we flipped it in half, the left side would match the right side. Okay, let's move on to a few examples. So here we have y equals the absolute value of x plus 1. So again, I'm just going to draw my parent function in blue. So that way it's a little bit easier to see the transformation. You may do the same, but this is not required. Okay, if we start plugging in points here, the absolute value of -2 plus 1 gives us 3. The absolute value of -1 is 1 plus 1 gives us 2. The absolute value of 0 plus 1 is 1. The absolute value of 1 plus 1 is 2. The absolute value of 2 plus 1 is 3. So here's our graph here. We can actually see, if we think about transformations from Topic 9, then we can see that this is pushed up 1. But another way that we could write this in order to identify the vertex just from looking at the equation is this is the same thing as y equals the absolute value of x minus 0. plus 1. So our vertex right here is 0, 1, which is why it is shifted up 1 right there. Again, if we were to fold this in half, we would have an axis of symmetry at x equals 0. And from our blue function to our red function, this is shifted up 1 unit. So that's our transformation. Next, if we have y equals negative times the absolute value of x minus 2, from this we can identify our vertex because this is the same thing as we're adding 0 on the outside. So my vertex here is 2, 0. Also noting from this, we have it's reflected over the x-axis because we have this negative sign in front. So we are also going to be reflected over the x-axis. And also from our vertex, if we just want to plot that, we're shifted over 2 units to the right. So let's just graph our parent function now. And if we wanted to plot our absolute value function, sorry, that was the bell. Let's plug in these values. So if we have negative 1 times the absolute value of 0 minus 2, that gives us positive 2 times the negative gives us negative 2. That is our vertex right here. Nope, it is not. That's a lie. That's our point right here. If we plug in 1 minus 2 is negative 1 times the absolute value is positive 1 times negative is negative 1. 2 minus 0 is 0 times an absolute value gives us 0, which that is our vertex. 3 minus 2 is 1 times the absolute value is, not times, the absolute value of 1 is 1 times the negative, it's negative 1. And 4 minus 2 is 2, the absolute value of 2 is 2, times the negative is negative 2. And we can continue this on our graph right here. Okay, so there's our graph there. We can actually see it is reflected over the x-axis. So zoop, turned over, and then shifted 2 units to the right. 2 more problems. Let's try y equals 2 times the absolute value of x minus 1. So this is really 2 over 1. I just want us to keep that in mind. And we can actually also rewrite this as y equals 2. And oh goodness, going crazy. 2 times the absolute value of x minus 0 minus 1. This makes it super handy dandy in order to determine our vertex. So our vertex is at 0, negative 1. So we can plot that right there. Let's plot our parent function just so we know what the original one looks like. There we go there. And from that, we can also see that it is shifted down 1 unit, so we can add that from our, in order to get to our vertex. And then we also notice that we have this 2 right here. So this is where we have a stretch by a factor of 2. Perfect. So let's plug in some values. Let's say we get negative 2, negative 1, 0, 1, and 2. The absolute value of negative 2 is 2 times 2 is 4 minus 1 is 3. The The absolute value of -1 is 1 times 2 is 2 minus 1 is 1. The absolute value of 0 is 0 times 2 is also 0 minus 1. There's our vertex right there. The absolute value of 1 is 1 times 2 is 2 minus 1 is also 1. And the absolute value of 2 is 2 times 2 is 4 minus 1 is 3. So we have our points here, and now we can plot. Okay, so there is our function there. We can also notice that we have an axis of symmetry. Oh, I didn't do that for the last problem. We can go back, don't worry. We have an axis of symmetry at x equals 0. Again, if we were to fold it in half and sandwich it, it'd be on the line x equals 0. Okay, now when we think about absolute value, see how we're multiplied by this factor of 2? This is really 2 over 1. So I want us to think about that when we think about our slope. So from our vertex here, what we're doing is we're going up 2 and over 1, up 2 and over 1, up 2 and over 1. Now because we have this axis of symmetry, it's going to be the same on the left-hand side. So we're just going to go up 2 and to the left 1, and that way it will match. But that can be really helpful because an absolute value function is just like a funky form of a linear function. Okay, let's go back to make that axis of symmetry because I did not mark that beforehand. Here the axis of symmetry is not at the origin or at x equals 0. The axis of symmetry is at x equals positive 2. So it goes right through the vertex. Last problem, we have y equals the absolute value of x plus 2 plus 1. So here we can easily see our vertex. Our vertex is at -2, 1. Remember, this is subtracting a -2, which is why it becomes positive there. So that is our vertex. We can plot our parent function. You know the drill by this point. Okay, and if we wanted to identify what our transformations are, we can look directly actually at our points right here. That plus 2 means it's going to be shifted left 2 units. And we're also going up 1 unit. So let's see that on our graph in order to verify that. Let's plug in the points -4, -3, -2, -1, and 0. If we take the absolute value of -4 plus 2, that's -2. Absolute value of -2 is positive 2 plus 1 is 3. -3 plus 2 is -1. Absolute value of -1 is 1 plus 1 is 2. Absolute value of -2 plus 2 is 0. So the absolute value of 0 is 0 plus 1 is 1. -1 plus 2 is positive 1. The absolute value of positive 1 is 1 plus 1 is 2. And 0 plus 2 is 2. The absolute value of 2 is 2 plus 1 gives us 3. Okay, so these are all of my points right here. And here's my vertex that I plotted. There we go. We can notice that our axis of symmetry right here, if we graph it, our axis of symmetry is at x equals -2. Wonderful. And again, we are shifted 2 units to the left and 1 unit up. That was topic 10 for Algebra 2 on absolute value functions. Thank you for watching.